Cryptography, the network immune system. Networks are inherently hostile environments. Every packet you send crosses wires and routers controlled by strangers. Cryptography is your immune system against 4 specific attacks. Eavesdropping, where attackers read your data. Tampering, where they modify your packets. Impersonation, where they pretend to be someone else. And repudiation, where they deny sending malicious traffic. The mathematical algorithms are perfect, but human implementation is always the vulnerability. Today we bridge the gap between abstract math and live packet defense. The 4 pillars of network crypto defense. Every cryptographic tool serves one of 4 pillars. Confidentiality stops eavesdroppers from reading your data. This is achieved through encryption, which scrambles data so only authorized parties can read it. Integrity stops tampering and unauthorized modification through hashing and HMACs. Authentication stops impersonation and man-in-the-middle attacks using digital signatures and certificates. Non-repudiation ensures accountability through digital signatures with timestamps. Every cyber attack exploits at least one pillar failure. Master these 4 pillars and you master security architecture. Symmetric encryption, the bulk data workhorse. Symmetric encryption uses the same key to encrypt and decrypt data. This shared secret approach is the fastest encryption method, ideal for bulk data encryption. AES 256 GCM is the industry gold standard, combining 256-bit keys with Galois counter mode. GCM mode provides both encryption and integrity authentication in a single pass. Modern CPUs with AES-NI hardware acceleration achieve over 10 gigabits per second throughput. The critical weakness is secure key distribution. How do you safely share that secret key across the internet? Asymmetric crypto and hashing, the negotiators. Asymmetric cryptography solves the key distribution problem. The public key encrypts data and verifies signatures. It is shared openly. The private key decrypts data and creates signatures. It is never shared. Elliptic curve cryptography, specifically curve 25519, beats RSA with smaller keys and 90% less CPU consumption. SHA-256 hashing produces a fixed 32-byte output and is mathematically one-way. You cannot reverse a hash. HMAC incorporates a shared secret key into the hash to prevent attackers from recalculating valid checksums. ECK key exchange, the forward secrecy engine. ECK is the crown jewel of modern cryptography. Diffie-Hellman allows 2 parties to derive an identical shared secret over a public channel without ever transmitting that secret. Ephemeral means session keys are generated fresh for each session and discarded immediately after use. Forward secrecy ensures that a 2026 key breach cannot decrypt your 2025 traffic because each session key is independent. TLS 1.3 mandates ECK and rejects static RSA key exchange. Without secure key exchange, you cannot establish a trusted encrypted session. The TLS 1.3 handshake, full packet flow. TLS 1.3 is the blueprint for secure network communications. The TCP three-way handshake establishes the connection with SYN, SYN-ACK, and ACK. The client hello sends supported cipher suites and the ECK public key. The server hello responds with the certificate, digital signature, ECK key, and finished message. The handshake completes in just one round trip. Encrypted application data flows immediately. The server certificate is now encrypted, hiding the website domain from passive eavesdroppers. Crypto across the OSI stack. Cryptography lives at different layers of the OSI stack. Layer 3 IPsec secures entire IP packets for site-to-site VPN tunnels. Layer 4 TLS and DTLS secure individual web and API sessions. Layer 7 MTLS secures internal microservice east-west traffic. Lower layer crypto is transparent to applications but broader in scope. Higher layer crypto offers granular control but requires application awareness. Enterprise defense uses all 3 layers simultaneously. The performance tax, CPU, latency, and MTU. Security always comes with a performance tax. CPU tax, AES-GCM is hardware accelerated while RSA is software bound. Latency tax, TLS adds approximately 2 round trips. 0 RTT session resumption slashes this delay for repeat clients. MTU tax, IPsec adds 50 bytes of overhead. If your encrypted packet exceeds the standard 1500 byte MTU, it fragments and firewalls often drop fragments. Always adjust the TCP maximum segment size. Monitor session resumption rates and handshake failure logs continuously. Network Crypto Decision Matrix. Here is your deployment decision matrix. For web traffic, enforce TLS 1.3 with EC and AES 256 GCM plus HSTS. For site-to-site VPNs, use IPsec with IKF2 and perfect forward secrecy. For internal microservices, deploy MTLS with 90-day certificate rotation. For Wi-Fi and LAN, use WPA3 for wireless and MACsec for Layer 2 Ethernet. The golden rule across all deployments: always enforce forward secrecy and always monitor certificate revocation via OCSP. Exam prep, critical scenarios. Let us review the 5 critical exam questions. Question 1. Why force TLS 1.3 over 1.2? Because it removes broken ciphers and mandates EC for forward secrecy. Question 2. How does HMAC defeat man-in-the-middle attacks? The shared secret prevents attackers from recalculating valid hashes. Question 3. Why is a compromised certificate authority catastrophic? Attackers can issue valid rogue certificates for any domain. Question 4. What is 0RTT and its risk? It speeds handshakes but allows replay attacks. Question 5. Where does crypto live in the OSI stack? Layer 3 IPsec, Layer 4 TLS, Layer 7 MTLS. Cryptography, the network